a machine worth over $200 million, weighing as much as 80 elephants, constructed from 6 million individual parts, and capable of carrying 500 people across continents at 600 miles per hour. Welcome inside the airplane factory, where one of humanity's most extraordinary engineering achievements takes shape before your eyes. The global puzzle begins. Building a modern commercial airliner isn't done in one place. It's a carefully choreographed global operation involving dozens of countries, hundreds of suppliers, and thousands of engineers working in perfect synchronization. Take the Boeing 787 Dreamliner, for instance. Its wings are manufactured in Japan by Mitsubishi Heavy Industries and Kawasaki Heavy Industries. The forward fuselage comes from Spirit Aerosystems in Kansas. The center fuselage barrel arrives from Alenia Aeronautica in Italy, and the vertical and horizontal stabilizers are built by Boeing in Frederickson, Washington. But how does a 50-foot wide aircraft wing travel halfway around the world without a scratch? Enter one of aviation's most bizarre-looking aircraft, the Airbus Beluga. This cargo plane looks like a flying whale, and it was specifically designed to transport massive aircraft components between factories. The Beluga XL can carry 51 tons of cargo in its enormous cargo hold, which has a volume of over 2,000 cubic meters. When Airbus needs to move wings from their Broughton facility in Wales to the final assembly line in Toulouse, France, the Beluga simply swallows them whole. The aircraft's nose lifts up like a visor, allowing entire aircraft sections to roll inside. It's a flying freight train for airplane parts, and without it, modern aircraft production would grind to a halt. But here's what makes this even more remarkable. These components arrive at the final assembly facility with tolerances measured in millimeters. A wing section manufactured in Japan must fit perfectly with a fuselage barrel made in Italy. There's no room for error, and that brings us to the factory floor where the real magic happens. Inside the world's largest building. The Boeing Everett factory in Washington State is the largest building in the world by volume. At 472 million cubic feet, it's so massive that clouds can actually form inside on humid days. The building covers 98 acres under one roof, large enough to fit all of Disneyland with 12 acres left over for parking. Inside this cathedral of aviation, 30,000 workers assemble some of the most advanced aircraft ever built, working in 3 shifts around the clock. Walking through the factory feels like entering a city. There are restaurants, medical clinics, fire departments, and even its own security force. But the real spectacle is the assembly lines. 6 separate production lines operate simultaneously, each building a different aircraft model. The 747, 767, 777, and 787 all take shape here, moving slowly along tracks at a rate of 1.5 inches per minute. Overhead, 26 massive cranes glide along 31 miles of track, lifting fuselage sections that weigh tens of thousands of pounds as if they were made of cardboard. The revolution of composite materials. Here's where modern airplane manufacturing gets truly revolutionary. Unlike older aircraft built primarily from aluminum, the Boeing 787 Dreamliner is 50% composite materials by weight. We're talking about carbon fiber reinforced plastics, materials so strong and lightweight that they've transformed aviation forever. The weight savings are staggering. A 787 weighs 15,000 to 20,000 pounds less than a comparable aluminum aircraft. That might not sound like much for a machine this size, but in aviation, every pound matters. That weight reduction translates directly into 20 to 25% better fuel efficiency and 20% lower carbon emissions. But manufacturing with composites requires completely different processes than working with metal. Instead of drilling millions of holes and hammering in rivets, composite parts are created through a process called autoclave curing. Picture a massive pressure cooker the size of a school bus. Engineers lay carbon fiber sheets over specially designed molds in a climate-controlled clean room. These carbon fiber sheets are pre-impregnated with resin called prepregs. Layer by layer, they build up the structure, with each layer oriented in specific directions to maximize strength. Once the layup is complete, the entire assembly gets sealed in a vacuum bag to remove any trapped air. Then it goes into the autoclave, where temperatures reach between 240 and 360 degrees Fahrenheit, and pressure builds to over 100 pounds per square inch. For hours, heat and pressure work together, causing the resin to flow through the carbon fibers and chemically bond into a single, incredibly strong structure. The result is a fuselage barrel or wing section that's lighter, stronger, and more resistant to corrosion and fatigue than anything made from aluminum. The Boeing 787's fuselage is built in large one-piece barrel sections, rather than being assembled from thousands of smaller parts. Traditional aluminum aircraft required countless rivets and fasteners, creating potential weak points and adding weight. The 787's composite barrel sections are essentially giant tubes with no seams, no rivets, just one continuous structure. This design allows the cabin to be pressurized to a higher level, giving passengers a more comfortable flying experience at altitude. The marriage of machine and technology. When those massive fuselage barrels, wings, and tail sections arrive at the final assembly line, they face their ultimate test. Everything must fit together with microscopic precision, and this is where 21st century technology takes center stage. Engineers use laser trackers and indoor GPS systems to position components with incredible accuracy. These aren't your smartphone GPS systems. We're talking about industrial-grade positioning technology that can measure distances up to 200 feet away with an accuracy of a few thousandths of an inch. At what Boeing calls Position 1, the final body join, all 5 major sections come together at once. 2 massive wings and 3 fuselage segments must align perfectly. The wings alone can weigh over 20,000 pounds each. To accomplish this feat of precision, engineers use a sophisticated jig called the final body join tool. This multi-armed apparatus cradles each component and uses laser measurements to position everything to tolerances tighter than the thickness of a human hair. Robots play an increasingly important role in this process. Diamond-tipped drills, cooled by fluid and powered by compressed air, bore thousands of holes through the composite materials. Each hole must be drilled in 3 steps to prevent damaging the delicate carbon fiber layers. The first pass creates a small pilot hole, the second enlarges it, and the third brings it to final size. Then titanium fasteners, each one torqued to exact specifications, join the sections together. On the 787, this process produces what Boeing calls the quiet bunch. Unlike the deafening hammer blows of rivet guns on aluminum aircraft, composite assembly is remarkably quiet, with only the whir of precision drills filling the factory floor. Miles of wiring and hidden complexity. Once the major structures are joined, the real complexity begins. A modern wide-body aircraft contains an absolutely staggering amount of wiring. The Airbus A380, the world's largest passenger aircraft, has 320 miles of electrical wiring running through its structure. Even the smaller Boeing 787 contains over 60 miles of wiring. To put that in perspective, that's enough wire to stretch from Los Angeles to San Diego. Every wire must be routed through the aircraft structure, connected to the right systems, and protected from damage. Installation technicians work in teams, threading bundles of wires through the fuselage, wings, and tail section. These aren't random bundles either. Each wire harness is carefully designed with specific routing paths, support clamps, and protective sleeves. Wires carrying different types of signals must be separated to prevent electromagnetic interference. Critical systems require redundant wiring that follows completely different paths through the aircraft, so a single failure can't disable essential equipment. The avionics systems alone represent a technological marvel. Modern aircraft cockpits are essentially flying computers, with multiple redundant systems monitoring and controlling every aspect of flight. The flight management computer, autopilot, navigation systems, engine controls, hydraulics, electrical systems, cabin pressurization, and hundreds of other systems all need power and data connections. Installing and testing all these systems takes weeks of painstaking work. Building the heart of the beast. While the fuselage assembly progresses, another crucial component arrives at the factory: the engines. A modern turbofan engine is an engineering masterpiece in its own right, containing between 20,000 and 40,000 individual parts. The Rolls-Royce Trent engines that power many 787s and A350s take approximately 20 days to assemble at the Rolls-Royce facility in Derby, England. The fan blades alone are works of art, carved from single pieces of titanium and hollow inside to reduce weight while maintaining strength. Each blade undergoes rigorous quality testing because a single failed blade could destroy an entire engine. When engines arrive at the aircraft factory, they're carefully mounted to the wing pylons using massive attachment points designed to hold engines that can weigh over 15,000 pounds each. But here's something fascinating. The engine mounts are specifically designed to break away in a controlled manner during a severe crash. This safety feature helps prevent the engines from penetrating the wing and igniting fuel tanks. After installation, each engine undergoes extensive testing. Engineers connect external power supplies and monitoring equipment, then fire up the engines while the aircraft remains secured in the factory. They monitor thousands of parameters: fuel flow, oil pressure, temperature, vibration, thrust output, and countless others. Everything must meet exacting specifications before the aircraft ever leaves the ground. The paint shop transformation. After months of assembly, the aircraft finally rolls out of the main factory and enters the paint hangar. This isn't your neighborhood auto body shop. Painting a commercial airliner is an intricate multi-day process that requires precision, patience, and specialized equipment. The entire aircraft first gets wrapped and masked to protect sensitive areas. Windows, sensors, antennas, and engine inlets all get covered with multiple layers of protective materials. Then comes the stripping process if it's a repaint, or surface preparation for a new aircraft. Workers spray a chemical wash over the aluminum or composite surfaces, then hand sand everything to ensure proper paint adhesion. The aircraft gets an acid etch treatment followed by alidine, a chromate conversion coating that prevents corrosion and helps paint bond to the surface. Next comes the primer, typically an epoxy chromate that provides corrosion protection. Then the base coat, which requires multiple applications. Depending on the paint system, anywhere from 2 to 6 coats might be needed, with the aircraft being baked overnight at 110 degrees Fahrenheit between coats to ensure proper curing. The paint booth itself is a technological marvel, with downdraft airflow systems that create perfectly clean conditions and prevent dust particles from ruining the finish. The stripes, logos, and airline livery come next, requiring meticulous masking work. Experienced painters apply each color, baking the aircraft between layers. Finally, a clear coat seals everything, providing UV protection and that glossy finish. The entire paint process can take 2 weeks and requires hundreds of gallons of specialized aviation paint. Every ounce matters. The paint alone adds between 600 and 1,200 pounds to the aircraft's weight, which is why engineers carefully calculate exactly how much paint is needed and no more. The final testing gauntlet. Now comes the moment of truth. Before any aircraft can be delivered to a customer, it must pass an exhaustive series of tests that would make most products seem like child's play. The testing phase begins with ground tests while the aircraft is still tethered to the factory. Every system gets energized and checked. The hydraulics are pressurized, flight control surfaces move through their full range of motion, landing gear extends and retracts dozens of times, and cabin pressurization systems undergo cycles that simulate altitude changes. Then comes taxi testing. For the first time, the aircraft rolls under its own power, with engines running and pilots at the controls. Engineers monitor every vibration, every sound, every reading from hundreds of sensors. Does the aircraft track straight? Do the brakes work properly? Can the pilots control it smoothly? Multiple taxi tests occur at progressively higher speeds until finally the aircraft is cleared for flight. The first flight is a carefully orchestrated event. Test pilots, some of the most experienced aviators in the world, take the aircraft through a predetermined test profile. They don't just fly around for fun. Every maneuver, every altitude change, every speed variation serves a specific purpose. They test how the aircraft handles at different weights, how it responds to control inputs, how the engines perform under various conditions. Data recorders capture thousands of measurements every second, creating a detailed picture of the aircraft's performance. Multiple test flights follow, each one pushing the aircraft a little further. Stall tests determine how the aircraft behaves at extremely low speeds. Flutter tests examine structural vibrations at high speeds. Emergency procedures are practiced, including engine failures, hydraulic failures, and electrical system failures. The aircraft must prove it can handle any situation safely. The delivery day. After months or even years of production, testing, and certification, delivery day finally arrives. The airline's technical team descends on the factory for their acceptance inspection. They scrutinize every detail with a fine-tooth comb. They review maintenance records, check for any cosmetic imperfections, and verify that every system operates exactly as specified in their purchase contract. The acceptance flight gives the airline's pilots and engineers their first hands-on experience with their new aircraft. They fly it through various maneuvers, test all systems, and make sure everything meets their standards. If any issues arise, Boeing or Airbus must address them before the airline will accept delivery. Assuming everything checks out, the paperwork gets signed, ownership transfers, and the brand new aircraft receives its certificate of airworthiness from aviation regulators. The airline's pilots then fly it home on what's called a ferry flight, often covering thousands of miles to reach the aircraft's new base. The entire process, from the first carbon fiber layup to final delivery, represents an extraordinary achievement of human engineering and manufacturing capability. Thousands of people across dozens of countries work together to create a machine that will safely carry millions of passengers over its 30-year service life. Every rivet, every wire, every composite panel plays a crucial role in this flying marvel. Your turn to fly. So there you have it. From global supply chains and composite curing to laser-guided precision assembly and exhaustive testing, that's how modern commercial aircraft are built step by step. The next time you board a plane, you'll know exactly what went into creating that incredible machine. Thousands of hours of human labor, millions of precisely manufactured parts, and cutting-edge technology all working together to defy gravity. What surprised you most about the airplane manufacturing process? Was it the sheer size of the factories, the precision required, or maybe the bizarre beluga aircraft flying wings across Europe? Drop your thoughts in the comments below. And if you found this deep dive fascinating, smash that like button, share this video with anyone who loves aviation or engineering, and don't forget to subscribe for more in-depth looks at how extraordinary things are made. Hit that notification bell so you never miss an upload. Until next time, keep looking up and wondering how it all works.